I'm happy to introduce Tong from Japan, speaking to us today about matroids and other things.
Thank you. Thank you for the invitation. Yes, so I will talk about the representation space of a matroid, and there are actually three different ways to describe that representation space, but for today's talk, I'll probably just focus on two of them, by hyperplane matrices and by the universal cross ratios. And in the end, I would only mention a little bit about a third representation of a third description of the representation space by the pairs of circuits and cocircuits. Okay, so I would like to assume a little bit background on matroids, but let me first review my preferred way of defining a matroid in this talk. So if we have a finite set E, my ground set 1 through n, a matroid on the ground set E is encoded by a set of hyperplanes, the script H, that is a collection of subsets of the ground set E, with the following three axioms. The first one is the entire ground set is not a hyperplane. And the second one is if we have two distinct hyperplanes, H1 and H2, then they cannot be subsets of each other. So they cannot have H1 containing H2 or H2 containing H1. And finally, the most important axiom says that if we have two distinct hyperplanes, H1 and H2, and if we have some element outside the union of H1 and H2, then we can find a third hyperplane H3 such that the H3 hyperplane contains the intersection of H1 and H2 union the distinct other element X. So you can view it, if you are familiar with matroid, you can view it as a dual version of the circuit elimination. Or if you like linear algebra, hyperplanes to a matroid are exactly the maximal proper subspaces to a linear space of the desired rank in the desired, say, f to the n with the n equals to the number of elements in the ground set. And once we have the hyperplanes, we can look at the intersection of hyperplanes. Those are called flags. And we can order those flags by the static theoretic inclusion. Then the flags of a matroid form a geometric lattice with a rank function. So the hyperplane will have co-rank 1, and the one smaller flags will have co-rank 2, and blah, blah, blah. And finally, the empty flag will have rank 0. Now, once we have a matroid with the set of hyperplanes H, there is a classical theory of representing a matroid by the hyperplanes. So you can find this proposition in Oxley's book. It is in the chapter of the matroid representation without a proof, but it gives a reference on this proposition. So if a matroid is representable over a field F, then we are able to find a hyperplane function fh, one for each hyperplane H, from the ground set E to the field F, such that we call it a hyperplane function because this function vanishes exactly on the hyperplane. So A, some element A is in H if and only if fh of A is equal to 0. So it is some function that vanishes on the hyperplane. And furthermore, the more important condition is that if we have three distinct hyperplanes, H1, H2, and H3, where the intersection is of co-rank 2, then the corresponding three hyperplane functions are linearly dependent. And that means we are able to find non-zero elements, C1, C2, and C3 in the field, such that the linear combination of the three hyperplane functions is a zero constant function. Now, once we have those hyperplane functions, one for each hyperplane, we call the collection of FH a modular system of hyperplane functions for the matroid M. And in particular, in the second condition, if we have three distinct hyperplanes intersecting at a corank 2 flat, then we say the three hyperplanes form a modular triple of the hyperplanes.
Question.
Yes, please.
So H1 intersection H2 intersection H3 can be of at most corank 3.
No, it can be any corank. So if, for instance, if the matroid has a very large ground set, and if it is of rank 2, then you may have empty, okay. Let's say large ground set and small rank. Then you can find a rank 0 intersection. That is, say, it has corank bigger than 2 or 3, bigger than anything you want, actually. So the thing is, you can have all possible corank intersection.
Okay. And does this hold for higher coranks too? The linear dependence?
Oh, yes. So this, if you allow larger corank, then actually you put stronger conditions on the matroid representation. So it is a pretty weak condition for which we guarantee a representable thing for the matroid. So it is nice because it is weak. Because we only need to look at the modular triple of hyperplanes. We only need to look at the 3 points on a coline.
Okay, cool.
Yes, thank you for asking. So just feel free to stop me and ask questions. All right, so let's look at one example. This will be the running example throughout the talk. So let's consider the uniform matroid U24 on the ground set 1 through 4. The hyperplanes are exactly all of the singletons. Let's say HI is just the set I. Then we give an F3 hyperplane representation by the following hyperplane matrix. So this matrix A has 4 rows and 4 columns. The rows correspond to the hyperplanes and columns indicate the elements. So how do we read this matrix? Well, in the first row, we have 0, 1, 1, -1. And that means for the function fh1, element 1 goes to 0, and element 2 and 3 goes to 1, and element 4 goes to -1. And similarly, you can read off the other hyperplane functions in the following second, third, and fourth rows. And you can use the direct computations to find out that it is an F3 hyperplane representation because, for instance, H1, H2, H3, they form a modular triple of hyperplanes. The intersection is its empty set is corank 2 because it is 2 minus 2 is 0. And the linear dependence is given by 1 times FH1 plus -1 times FH2 plus -1 times FH3. It's the 0 function. So we get 0 for all elements simultaneously once we do the linear dependence. Now, our question here is, how do we find out all of the possible representations by the hyperplane functions of a matroid? And actually, let's do it in a more generalized format. Let's look at the representations, not just over a field, but over a more general algebraic structure that we call a pasture. So a pasture will encode the information for the linear dependence. So we say that there are only 3 terms for the linear dependence. So we only record the information when 3 elements sum up to 0. So a pasture P consists of those information. First of all, the unit group is a multiplicative written abelian group, P star with multiplication and some neutral element 1. And we also have an extra multiplicatively absorbing element 0, so that 0 times A is always 0 for every element A in P. And we also have an involution -1, this is also a unit such that -1 squared is the neutral element 1. And the most important thing is the additive structure on the pasture. So additive structure is not a binary operation, but a subset of p to the 3. So it is a triple of elements in the pasture P, and the P is just the units union the 0 element. And this add structure is determined as follows by the following axioms. The first one is NP is closed under the natural action of the symmetric group of P3. So for instance, if 1, 2, 3 is in NP, then 2, 1, 3 and 3, 1, 2 are also in the additive structure NP. So it is somehow the commutativity of the addition in the usual sense. And secondly, NP is closed under the multiplication of the pasture. So if you have 1 plus 1 plus 1, 1 comma 1 comma 1 is in NP, then A comma A comma A is also in NP for every element A in the pasture P. And finally, it is the additive inverse axiom. So if we have so x comma y comma 0 is in NP, this happens if and only if x is equal to the -1. And negative y here means the -1, the involution, times y. All right, we call the additive structure NP the non-set of the pasture P. And if we have x comma y comma z in NP, we by abuse of notations write x plus y plus z is equal to 0. So they say it's a abuse of notations because really we do not mean that x plus y plus z is equal to 0 as an element, but we mean that x plus y plus z is a non-expression. So for instance, if you have x, y, z in the non-set, and we do not have x plus y plus z plus x plus y plus z is equal to 0. So that's not happening here. So we only record the 3-term additive relations, that is a non-expression. Okay, let's do a few examples. Okay. So before the examples, probably let me define the morphisms. So if we have two pastures P and Q, a morphism is, first of all, a multiplicative map from P to Q. And secondly, it takes 0 to 0, 1 to 1. And then if we have x plus y plus z equals 0 in P, then the images fx plus fy plus fz is equal to 0 in the second pasture Q. So we respect the multiplication and the non-set additive structure of the pastures. And let's do a few examples. For instance, the regular partial field, which has something to do with the regular matroids. The elements are 0, 1, and -1, and the non-set quotient by the S3 action has two elements. The first one is 0, 0, 0, and second one is 1, -1, 0. But you can do the S3 action on it, so it also has 1, 0, x -1, etc. So it is the initial object in the category of pastures. So this is our first example. And if we go back to the classical theory, if we study a field F, then this field F, every field F is naturally a pasture with the same set F. And the non-set is given by x, y, z, where x plus y plus z equal to 0 as an element of the field F. And finally, the final object for the pastures is what we call the Krasner hyperfield. It has two elements, 0 and 1. And the non-set has, again, modeled by the S3 action, it has 3 elements. the all 0 thing and 1, 1, 0, and all 1 triple of in the P3. Now, if we do the cluster hyperfield, then every matroid is representable over this K, because how do we give hyperplane functions? Well, if we take some hyperplane H, then fH of A is equal to 0 for all A in the hyperplane, and fH is equal to 1 for all elements A outside the hyperplane, because there are only 2 elements, and by the axiom 1 of the hyperplane functions, it is uniquely determined, and it is a modular system of hyperplane functions. You can check it out in for the second axiom. So we will use the null set NP to capture the linear dependence relations between the hyperplane functions. So how do we do that? Well, we can just simply replace the field F by a pasture P in our first proposition. Then we immediately get the matrix representation over pastures by the modular system of hyperplane functions. Now, before we construct all possible representations, let me first do some equivalence relations on the representations. So why we wish to do that? Well, if we go to the classical case, if we are about to represent a matroid, say by a matrix, then of course you can do the row operations of the matrix, and then you get the same row space, but different matrix, but you still have the same matroid outside of this matrix or the linear space. Furthermore, if you rescale certain columns by some non-zero elements, you probably end up with a different linear space, but you still get the same matroid outside this rescaled matrix. So we wish to respect this rescaling of columns. So even if we are representing a matroid using different spaces, we are still lying on the same orbit of the toric action on the grass onion. So that is how we wish to put this rescaling equivalent on the hyperplane representations. So in our case, we say two representations by the modular system of hyperplane functions are rescaling equivalent if we can find non-zero scalars, say H and say E, one for each hyperplane and one for each element, such that the second hyperplane function fH prime is equal to this global scalar CH times the product of CE for all E outside H times our first hyperplane function fH. And this can be done simultaneously for all hyperplane H for the matroid M. And now we call the set of, we denote the set of all rescaling classes of representations of M over some pasture P by chi M over of some pasture P. Now, our goal, let's say our ultimate goal is to obtain all of the possible rescaling classes of representations inside chi M. Now, we wish to determine a representation, so we only need to determine fH at A for all A outside the hyperplane H and for all H in a hyperplane of the matroid M. So let's do it in, say, 3 different ways of this problem. And the first way is kind of a continuation of the previous example of the uniform U2-4 matroid. So let's say I have a matroid M in general on some ground set E. We first construct a bipartite graph GM. The vertices are the hyperplanes and the ground set E, where a hyperplane and an element are adjacent if and only if A is not in the hyperplane H. So that means our hyperplane function evaluated at A is not 0. So this is our bipartite graph for U2-4. So if we look at all of the edges, both in red and in black, we have the G of U24. Now, step 2 is to choose a spanning forest of this graph. And here by the spanning forest, we mean the maximal subgraph without any cycles. Now, the red edges give us a spanning forest. For instance, you say H1 goes to 2, goes to H3, goes to 4, goes to H2, goes to 3, goes to 4, H4 goes to 1. So there's no cycle in this spanning forest, actually, the spanning tree. Now, once we have a spanning forest or spanning tree, we set the hyperplane function fh is equal to 1 for every element A if HA is an edge in the spanning forest. So this is somehow the rescaling part. So we fix some rescaling in the representation. Now we have some values of the hyperplane functions, and now we need to determine the remaining things. Now, how do we do that? Well, we just put relations on the remaining values, and that will suffice to determine all the representations of the matroid M over an arbitrary pasture P. So before that, let me fix some terminologies. So we say a 3x3 matrix T, if it has 2 zeros in skew positions. For instance, if you have zeros at I1, J1, and another 0 at I2, J2, then we need I1 is not equal to I2 and J1 is not equal to J2. So it is the row index are different and column index are also different. So it is what we call the skew positions. So there will be another example later. Now the matrix A, after the first steps, we wish to complete this matrix, and the completion will give a modular system of hyperplane functions if and only if we look at all of the TIM 3x3 submatrix whose rows correspond to a modular triple of hyperplanes, then we must have that determinant is equal to 0. So let's look at 2 remarks on this theorem. So if first of all, we are working over pasture P, and we only know when a 3-term expression is null. And so if P is TIM, then its determinant will have at most 3 terms. So the determinant is equal to 0 makes sense over pasture P. So that is, we put TIM here to guarantee that once you write out the determinant, it is either some null expression or it's not a null expression but still has 3 terms. So we can say when the determinant is equal to 0 or not. And secondly, in this theorem, we do need to look at all of the TIM 3x3 submatrices whose rows are modular triple of hyperplanes. But actually, there is a refinement of this theorem so that we only need to check a smaller number of TIM submatrices. And this smaller number is actually equal to the number of non-determined values of the hyperplane matrix. So there are actually a smaller number of relations on those undetermined hyperplane function values. Okay, for instance, let's continue with our example of U24. So after step 2, so remember in step 2, we have a spanning forest or the spanning tree in our case. The red edges are the spanning forest. For instance, we have an edge, H1 and 2 in the spanning forest. So we put H1, 2, the number 1 here for our representation. And we have some other edges in the spanning forest. We always put 1, so that is our step 2. Now, for step 3, we look at the TIM matrices. For instance, the lower right part, 0, 1, 1, 1, 0, 1, E, 1, 0, is a TIM submatrix. it has actually 3 zeros in skew positions. So those 3 zeros are in skew positions because, well, they have different row and columns index. And because we require that this matrix over P is singular, so we know the determinant, this is 0, this is 1, this is plus E, minus 0, minus 0, minus 0. So we have 1 plus E has to be equal to 0. So from the step 3, we know E must be equal to 1. And similarly, if we look at the TIM matrix on the upper right part, it is an honest TIM matrix with only 2 skew zeros, here and here. And we look at the determinant, it is equal to 1 plus A minus B. And we know this is a null expression, so 1 comma A comma negative B is in NP. And we get another relation for the for those undetermined hyperplane function values. That is 1 plus A minus B is in the non-set, or is one of the null expression. And in fact, if you do all of the computation for all of the 3x3 TIM submatrices, then you can find out that the elements C, D, and E are all determined by A and B. So over an arbitrary pasture P, the rescaling classes of representations will be given by the morphisms from this particular pasture to P. So what does that mean? That means once we give values in P for this entry and that entry, and if we furthermore assume that this that is A and B satisfies the relation that 1 plus A minus B is equal to 0 in the pasture, then we are able to give a representation of A over the pasture P, because then the other undetermined things are actually determined from A and B. So this is a general fact that the functor chi-m that takes a pasture to the set of all rescaling classes of representations. This functor is representable by a pasture fm attached to the matroid m. And in this case, for the U24, the f for the fm for U24 is this pasture. It is the regular pasture field joined with 2 more variables that satisfies this additive relation, the extra additive relation. And we have the set of all rescaling classes of representations is actually in bijection with the morphisms from Fm to P. And we call Fm in the theorem the foundation of the matroid M. And actually, from this hyperplane matrix approach, we are able to describe the foundation Fm from some smaller number of undetermined hyperplane function values and from the TIM 3x3 submatrices. So this is somehow computationally efficient because it is just some linear algebra. So we just form the bipartite graph and we choose the spanning forest, and we just complete the matrix with some ones and undetermined values. Okay.
Tong,
Yes.
can you remind me what do A, B, like what do the variables here tell us? I guess it tells us that the function. Yes.
Yes, right.
Just
so we
Yes.
wish to obtain a representation, and the representation is given by a modular system of hyperplane functions. So to give a representation, we must give values of the hyperplane functions. For instance, for the first hyperplane function fh1, after step 2, we know fh1 at 1 is 0, fh1 at 2 is 1, but we do not know fh1 at 3, and we do not know fh1 at 4. So those are the undetermined, those are the to be determined values of the hyperplane functions. And the theorem here says, once you know, or the example here says, once you know the values of A and B, and once those values satisfy the relation that 1 plus A minus B is equal to 0, then actually you can guarantee a representation of U24 over the over your choice of pasture P. So you can view it as the generators of the foundation, and that is the only relation inside the foundation. Or how do we give a representation? Well, we only need to give the value A and B here that satisfies this relation. Then if we're able to do that, then we're able to give a representation. And that gives us all of the possible rescaling classes of representations.
Okay, great. Thank you so much. I just needed a moment to reorient it.
Say the generators of the FM. The generators are the undetermined values, and the relations are from the 3x3 term minus term sum matrices. All right. Now let's go to the second approach. The second approach is kind of technical, and it requires some more combinatorial fact about matrices, but it tells more about the structure of the representation space. It tells us more about the set of all rescaling classes of representations of a matroid in terms of only the very small minors of the matroid M. So let's start with a matroid with a modular system of hyperplane functions fh taking values in a pasture P. Now a cross ratio of the matroid M has the following form. So we start with two hyperplanes H1 and H2, and we assume that H1 intersect H2 has corank 2. And we assume furthermore that we are able to find elements A and B outside of H1 and union H2. And A and B here can be the same, but if you wish to get a meaningful non-degenerate cross ratio, you probably want A is not equal to B. Now the cross ratio is given by the quotient of FH1A times FH2B over FH1B times FH2A. So it is why we call it cross ratio, because in the most generic case, if we have H1, H2 two hyperplanes intersecting at a corank 2 flat L, and if we have two other elements outside the union, then we immediately get two other hyperplanes. And those are given by H3, that is the closure of L and A, and H4, the closure of L and B. So in the most generic case, if H1, H2 are not different, are distinct, and if A and B are distinct, then those four hyperplanes are actually different. And in the lattice of flats point of view, you can view it as 4 points on a coplane or on a coline. That is why we call it a cross ratio. It can be viewed as a generalization of the cross ratio in the projective geometry. Now, once we have the cross ratios, our question here is, can we describe the foundation, or can we describe the representation space in terms of the cross ratios? And the answer is yes. And actually the foundation Fm of a matroid is generated by the universal configurations inside the lattice flats. So we don't care about the pasture P, we only care about the matroid. So once we have a matroid, we look at its lattice flats, and we look at the sublattices in the lattice. So we have four distinct hyperplanes, H1 through H4, and they all intersect at a corank 2 flat L. And that is what we call a universal cross ratio. So it is independent of the choice of pasture P. Now the foundation Fm is now generated by all of those configurations, by all of those universal cross ratios, or you can view it as a U24 minor inside the matroid M. And furthermore, those are the generators. Furthermore, the relations between those universal cross ratios or the relations between the U2 minors are given by the embedded minors of the matroid M on at most 7 elements. And there is actually a finite list of those small minors, which I will talk about later on. But the theorem confirms that you can actually obtain a modular system of hyperplanes once you know the values at the cross ratios, and once you guarantee that the relations among those cross ratios are satisfied. So how do we do that? So how do we construct a modular system of hyperplane functions outside of these universal cross ratios? Well, let's do the only partial proof. It is not complete, and we also assume a few combinatorial facts about matrices. So our goal here is to determine FH at A for all element A outside the hyperplane H. And we will do it by induction. And actually it is not that preferred, because you see in the previous approach, when we do the hyperplane matrix, it is quite direct and we do not rely on induction. So we just complete the matrix immediately. But now let's do the induction, and let's pick some element A in the ground set for the induction. For simplicity, let's assume that the matroid M and the deletion M delete A are both connected. Now the induction step, what do we do for the induction step? Well, the proposition here is that every rescaling class of modular system of P hyperplane functions, FH, for the matroid M is determined by the restriction of this hyperplane function to the deletion M prime and the values of cross ratios involving this separate element A. And well, it's just induction step. So let's say, how do we do that? So if we know the hyperplane function on the deletion, and if we know the cross ratios, now we wish to determine the remaining undetermined hyperplane function values. And there are, by case analysis, there are 3 hyperplanes to be considered. The first one, let's call it type A, is that A, the individual picked element A, is not in the hyperplane H. And if that is the case, then by some basic facts about minors of matrices, we know H is a hyperplane of both M and M prime. And now, because H is also a hyperplane of M prime, and because we know the restriction of the hyperplane function to the deletion M prime, the only thing we need to do is to find out FH at A for type A. So for type A, we only need to find FH at this picked element A. Now for type B is when the element A is in the hyperplane H, but the deletion H minus A is a hyperplane of M prime. So it is the easiest case because we know if H is a hyperplane of M and H minus A is a hyperplane of M prime, then we can get FH for the matroid M just from the hyperplane function FH minus A from the hyperplane function of M prime. And because we can just set FH at A to be 0, that is our first axiom of the hyperplane function, because A is inside the hyperplane. And the last case is when A is inside hyperplane, but the set H minus A is a corank 2 flat. This is a third case when, in this case, we actually say a modular triple of hyperplanes inside the matroid M. So let's probably just skip this one for the proof. So I will only do the proof for the type A case. So for induction, I will show you an idea on how do we get, let's say, an algorithm on how do we get FHA for H in the type A hyperplanes. Okay, so we rely on some combinatorial structure of the matroid and the matroid deletion. So let's denote H prime, the set of hyperplanes of the deletion M prime. We construct a Tong graph. So Tong graph, the vertices are exactly the hyperplanes of type A. Or in terms of the hyperplanes of the deletion matroid, those are the hyperplanes in the deletion so that A is not in the closure of H. So this closure is the closure in matroid M, but not the deletion M prime. And two vertices or two hyperplanes of type A are adjacent if H1, H2 intersect at a co-rank 2 flat, and if their union is not everything in the ground set. So we are able to find a third hyperplane of type A to give us a modular triple of hyperplanes in the deletion. And these vertices are precisely the hyperplanes of type A in the induction step. And the two lemmas or the two theorems says the first one is a path theorem. So if M and M prime are both connected, then the Tong graph is also connected. So that means if by some simplistic assumption that if we assume M and M prime are connected, then if you start with one hyperplane of type A, then you can go from this hyperplane to all of the other hyperplanes of type A through a path inside a Tong graph. And that is the path theorem. It is a special case of the fundamental theorem of the convex subclasses of matrices. And the second theorem or second lemma that we use is a homotopy theorem that says every cycle in the Tong graph can be decomposed into 3 different types of elementary cycles. So that means, for instance, if we connect two hyperplanes of type A by 2 different paths in the Tong graph, then we can actually decompose that cycle into smaller cycles of length at most 4 here. I didn't mention that in the statement of the theorem. So every cycle in the Tong graph can be decomposed into 3 different types of elementary cycles of length at most 4. So once we are equipped with those 2 lemmas, let's say how we can give a modular system of hyperplane functions. This is only a partial proof for the type A hyperplanes. So we first fix an arbitrary H0 of type A. And let me recall that the hyperplanes of type A are such that A is not in H. So the hyperplane H is a hyperplane of both M and M prime. So we first fix some initial point, and we set FH0A to be 1. Now, let's say we have some arbitrary other hyperplane of type A. Then we only need to determine FH at A. And now by the path theorem, we can find a path using the hyperplanes of type A. Let's say H1, H2 up to HK is equal to H. With the property that intersection is of co-rank 2, and the union is not everything in the deletion. So if we wish to determine FH at A for H in the type A hyperplane, we only need to prove for the case when H0 and H are adjacent in the hyperplane in the Tong graph. So let's here assume that the intersection has co-rank 2, and H0 union H is not E minus A. But now from this very restricted assumption, this is quite straightforward because we can just pick an arbitrary element outside the union. Then FHA is just determined by the cross ratio H0, A, and B, and the known values of FHB and FH0B. And those values are known because we already know the hyperplane functions, or we already know the representations of the deletion M prime. And those are already inside the M prime. And so that is somehow guaranteed a unique representation once we know the cross ratios and once we know the restrictions. But there's another thing that we need to worry about is that do we always get a honest representation, or do we always get a well-defined representation? Well, that is why we do need those relations. And actually the relations among the cross ratios come precisely from the well-definedness of these representations. And for instance, we did for type A 2 different choices. We had to choose a type path. And we also have to choose some element outside the union of the two hyperplanes. Now, for instance, if we look at if we have two different choices of element outside the union, then the cross ratio actually, the value of FH2A is actually does not depend on the choice of the actual element you pick outside the union. And this relation corresponds to a U2 minor in the matroid F. And one intuition on why this is U2, well, because we have H1, we have H2, and let's say we have two extra elements B1 and B2 outside the union, then we already get H3 at the closure of the intersection B1 and H4 at the closure of the intersection B2. So we have two more hyperplanes. And inside the matroid M, we also have the closure of intersection and the extra element A. So somehow, intuitively, there are 5 hyperplanes intersecting at a co-rank 2 flat, and that is a U2 minor. And that gives us one of the relations among the universal cross ratios. And the other thing we need to worry about is the path. So once we can pick 2 different paths in the type graph, so we do get a cycle in the type graph. And by the homotopy theorem, we can decompose the cycle into smaller elementary cycles. And if you analyze on the condition of those vertices on the cycles, we can actually see a few smaller minors in the matroid. And those are isomorphic to either U24 or U35 or the funnel or some graphic matroid from the complete graph K4 minus some edge. And finally, the dual funnel matroid. And from that, we can guarantee that we get a honest, well-defined hyperplane function representation of the matroid M. And this is kind of the partial proof for the type A hyperplanes. And for type C, it is actually simpler than type A case. So let me just skip that. So there is a third approach of the representations, but let me how much time do I have here?
You've got a couple minutes.
Okay. So let me just mention that. So let me do a comparison of the different approaches. So the first approach, the hyperplane matrix approach, is easier and direct for computations because, well, we do not need, say, inductions. We do not need to worry about whether the matroid is connected or not. And we just construct the bipartite graph and we just complete the matrix. It is almost linear algebra. While the second approach, the cross-ratio approach, tell us more about the structure of the representations. And actually it tells that if your matroid, for instance, has no U2 minor, so it has no generators at all, then the representation space or the foundation is either the regular partial field or a quotient of the regular partial field. So it is either F2 or the F1 plus minus. And there are some other few applications of the second approach. that is pretty powerful, but in practice, you probably don't want to construct representations out of this approach. Now, there is a third approach by circuits and cocircuits. And similar to the hyperplane function, you can give circuit functions and cocircuit functions. And in that approach, the generators are given by also a ratio of the form, say, D, X, and Y. Here, say the circuit. D is a cocircuit, and X and Y are elements in the intersection. And the generator is given by, say, X times dx over, say, Y times dy. Now, those are somehow redundant cross ratios. So the relations, the multiplicative relations among those generators are only the obvious ones. So say you have X, Y, and Z in the intersection, then you get the obvious CD XY, CD YZ, CD ZY. The product is equal to 1. And probably one also some degenerate case when X is equal to Y or something that. So the multiplicative relations on this approach are only the obvious ones. And the additive relations are from the orthogonality between the circuit and cocircuits. Here we mean that the intersection of a cocircuit and a circuit cannot be of size 1. And you can give some inner product on the circuits and cocircuits, and that gives you the additive relations. And that is the third approach. But this is somehow known results. Let me just briefly mention that. So there's some other methods. And that's it. Any questions? Are you muted if you are speaking?
No, but thank you for a great talk. Yeah.
Yeah.
Questions?
I had a question, which is your like chi m of p. That's the notation I'm used to for like the characteristic polynomial of a matroid. Is it related to that, or is it?
Oh, I'm
like,
sorry. Yes. It is not the characteristic polynomial. It's not a polynomial. It
right.
is
Yeah, I
not a
just didn't know if it was
polynomial.
related in any way. Okay.
Yes. Well, I'm not sure. So there are different ways of giving the representations. So probably the way that I prefer is by these hyperplane things, but probably you can do by flats, and that has something to do with the characteristic polynomial. But there are those. One thing is polynomial, and here it's just a representation space. It's a collection of all representations.
Any others? Maybe if there are no others, stop recording. You can thank Tong again.
Thanks again for the invitation.